Hi, my name is Debbie Bazina. I'm the Managing Director of the Center for Connected and Automated Transportation. I'd like to welcome everyone to this special CCAT seminar series featuring Central State University. The On the Road to the Global Symposium is a series of webinars we are hosting in the lead up to the CCAT Global Symposium on Connected and Automated Transportation. We hope you were able to join us this past Tuesday for the automated brine application presentation from Professor Darcy Bullock of Purdue. If you missed it, you can watch the entire presentation by going to the Center for Connected and Automated Transportation YouTube channel, which is linked in the chat. The 2020 CCAT Global Symposium is scheduled for next Tuesday, April 14th, and will feature discussions with leaders from academia, government, and industry, covering topics such as the 5.9 gigahertz spectrum reallocation, cybersecurity concerns, and infrastructure changes. Tickets are extremely limited, and registration can be found at ccat.eventbrite.com. Today's webinar is led by Professors Nedunuri and Ramani Kandiah of Central State University. Dr. Nedunuri is a professor of environmental engineering in the Department of Water Resources Management. He's also the director of C.J. McLin International Center for Water Resources Management. He got his Ph.D. in environmental engineering from Purdue. He is a STEM fellow at the Dayton Regional Center and a scientific teaching fellow at the Summer Institute, organized by the National Science Foundation and Howard Hughes Medical Institute. Nedunuri also teaches graduate courses in clean energy engineering at Wright State University. He served as PI and co-PI in over 25 research and education grants, and is a reviewer for the NIFA and for professional journals. He is a member of the State Technical Board and for the National Resources and Conservation Service. Dr. Ramani Kandiah is a professor of environmental engineering in the Department of Water Resources Management at Central State University. He holds a Ph.D. in civil engineering. He is a registered professional civil engineer in Ohio, certified professional hydrologist, board certified environmental engineer, and Envision Sustainability Professional. Wow, that is a lot. His research interests includes transportation-related air and noise pollution modeling and environmental impacts of renewable energy. This presentation will include a Q&A seminar at its conclusion. To ask your questions, please submit them in the chat window of WebEx or go to menti.com, MENTI.com, and enter the code 92-70-37. Please mute your microphone for the duration of this presentation. Without any further ado, let us begin.
Hello, everyone. Good afternoon. Thank you so much, Debbie, for giving that long introduction, though we probably don't deserve everything, but, well, everything there is true, though. Again, I want to make sure that everyone could see the slides that we have in here. So we're going to dive into the presentation without any introduction. Very quickly, our own project is looking at greenhouse gases and, of course, priority pollutants in the air. The whole idea is to see, if we can get a very simple app. That's our goal, to have a very simple app where, in addition to the traffic alerts that one can always access, we can also look at air quality, and more importantly, at the congested areas, where you are approaching that congested area, and then on your cell phone, you could, ahead of time, see how intense the air quality or air pollution is, and then make some judgment as to whether you still want to pass through those intersections or try an alternate route, so that you are traveling through clean air, but also you are trying to protect that particular busy intersection. So that being the long-term goal. Next slide, Ramani. So that being the long-term goal, I want to take you on a journey as to why we're doing what we're doing here. So let us look at the congestion itself. Going back to 2000, you can clearly look at, how big an expense it is. You're looking at a $31 billion, enterprise, in terms of the monetary value, associated with, traffic congestion and air pollutions, more on in urban centers. And also look at the, these congested areas and how much time delays and then fuel consumption, that's of the order of 60 billion, that's back in 2000 data. Just to give you a breadth of the problem as far as congestion is concerned, but then, you go down and then you look at 2020s and 2030s, you can clearly look at, the enormity of the situation, public health wise, looking at $13 billion, that was projected into 2020, which is where we are now. And in 2030, it's going to go into $100 billion. So you're looking at the scale of the problem here, so that just tells you how important it is, to have, this type of work, we are really going to, manage these congested areas, if we do it right. So connected and automated vehicles, is a possibility, that's one solution to this problem, of controlling, congestion as a whole. But then, our specific focus and what we add value, to the center in terms of dealing with traffic congestion is to look at these, greenhouse gases, and we all understand, the global drivers, for controlling the air quality and then carbon emissions. So at one scale, we are contributing to reducing the carbon emissions and at a global scale. Also on a human and person scale, we are attempting to improve the air quality, using by embedding, this small app, into the overall app, that these vehicles would have in future. So Ramani, can you lift the slide up a little bit? For some reason, the font is very small from the screen that I'm looking at. So looking at, so that being the background, I want to give you an idea as to, historically, how we have moved in terms of incorporating, emissions into these models. So if you look at the, early models, they are trying to incorporate the severity of emissions, into models by just looking at factors. We call them emission factors. So that is the preliminary work, of accounting for traffic pollution in congested areas. The problem with those kinds of early models, is that they don't incorporate the real-time data, in terms of the traffic density that we have, and also local conditions. So those are earlier models, obviously they needed improvement. But then, slowly advances have been made possible in terms of our ability to understand traffic, and also get traffic data, and also ability to really run models, that could represent some realistic information as far as the emissions is concerned. So the whole idea is, if we can incorporate, such a model into autonomous systems, even a small fraction, looking at 5%, how is that going to, dampen the traffic waves, So in that, if you can reduce the congested area, by giving alerts ahead of time to approaching traffic, and then make them some pretty wise decisions as to not to further congest those areas, So what that would lead to is, a reduction in, traffic waves. The stop and go waves would be reduced, and then, that would, probably result in reduced emissions. So that's where we're going, in terms of modeling. So where we are right now is to, get some more realistic picture into these models, So how do we get there? Next slide. So the overall idea is to, develop this app, but then taking into consideration the real-time data that becomes now available. And Ohio has it. I don't know if you can see on the background. I'm looking at a traffic monitoring system that Ohio Department of Transportation provides us, which gives us not only information on AADT, but also on the volume of traffic. So we are getting that information now available real time on one hand. On the other hand, moves, for some people who don't understand move, who don't have the full acronym of what moves is motor vehicles emission simulator. So that model has been evolving, on several directions, and it is going to provide you some realistic, information on how much, you would expect, emissions, how much of emissions you would expect in a traffic congested area. So given real-time traffic data and some realistic estimations, from the moves, we would be in a better position to estimate, how much emission would be occurring, from those intersections, we call congested areas. But in many cases, models probably have stopped right there. To me, that wouldn't be, a complete story. So it's one thing to have a sense of how much emission is coming from those tailpipes. But then, for someone who is, not in the congestion, but who is approaching the congestion, maybe, 10, 15 minutes away, for that person, more important would be the ambient air pollution. And because he would be seeing that ambient air pollution, but not the pollution from the tailpipes of the vehicles which are currently in the intersection. So the whole idea is get that information, traffic information, and also the information from the moves, calculate the emission, but from there, using some simple dispersion models, we should be in a position to calculate how much of that pollutant being emitted from the traffic will be in the ambient air, persistent for some time, And if that information could be relayed to oncoming traffic through their cell phones, that would be useful information. So, in order to get there, you do need some data, from the environment. You also need to understand, some geometric data as to wind direction in relation to the, road. So that information is also needed. And, given all that inputs, the whole idea is to arrive at a very simple dispersion model, that will take this emission and then calculate ambient air, pollution. Next slide. This is a nice algorithm, showing the methodology we would be using. So we would get the location, exact location from GPS, which is very easily available from the cell phones. And then we'll put that in the GIS mapping to locate the intersection, where the traffic congestion is taking place. So once we have that information, we will load, from the server, the most available data, currently available data from our traffic management systems that, that each individual state, has. Ohio has. We know that, it's available with ODOT. So we take that information and then be able to run the moves model to get some estimates of, both greenhouse gases and also the ambient air quality, pollution, like carbon dioxide, NOxes, SOxes. So all that information, the moves would give us an estimate. And in many cases, we can also come up with some innovation as to, look at that data that already has, in the system. So we would have run moves ahead of time and have that system already available, So a combination of real time and existing information on traffic is what we would take and then run moves. And as moves estimates, we will take that information as source and run the dispersion model. and be able to calculate ambient air, air quality, both in terms of greenhouse gases and also the air pollutants, material air pollutants. And then, eventually you can present that information in a visual GIS form, and then have it available in the app. Next slide, Ramani. So that's the whole strategy of solving this particular problem, and then be able to create a traffic alert in terms of air pollution. If you look at what kind of data that we would be focusing on, as you see, our focus is going to be on trucks, and also passenger vehicles. And if you look at the traffic monitoring systems, and they have these stations that are available. You see, a typical traffic monitoring system. You're looking at I-70, I-75 intersection, and all these blue dots are essentially stations, where the volume of traffic is already available. So you have that information, and then ADT. So this is the traffic monitoring system that you're seeing right now. If you can see on my screen, it's behind me, it's on the presentation. That's a typical I-70, 75 intersection. And the monitoring system on the left-hand side is providing you the data. Everyone can see that slide. It has ADT available, but most importantly, it has volume data, which is more realistic. And it also, segments the traffic data in terms of the speed, the class of vehicles. So this information is available to us, and we could use that information to calculate the pollution emissions. Next slide, please. All right. So once we have that real-time data, we run moves. Ramani, can you go back one slide? I want to also, spend some time on the moves model itself. So this is the moves model. Again, it's an exhaustive model. It takes into consideration all types of vehicles, all types of fuels. It gets information, on traffic across the nation. So we have all that information embedded into moves. It takes all that information, and it calculates, the priority pollutants, greenhouse gases, and also air toxics. So it spills those numbers in terms of emission amounts. But the important thing is, as you see across columns, it also generates that information, across several stages, in the combustion. It gives information at various points, along the vehicle system. So that's a very intense model. But the key thing is it takes a long time to run. So our strategy is to run this information offline, since we already know the kind of intersections that we are going to work on, and keep the data, in a nice database, to be retrieved. So that's our strategy. That's what makes our model very unique. To move, to strategically run the moves offline, get that information on emissions, and use current traffic data, to modify our emission estimates in the congested area, and then calculate how much is present in the air. Ramani, go ahead. Keep going. Back up one slide, please. So you see, the key thing, in an app is to have as simplified models as we can. We know that these Gaussian dispersion models can be intense, but the whole idea is, can a simplified model, still be in a position to give you, an order of estimate, values that we could use and that are realistic. Go ahead, Ramani. Next slide. So so that simplified model can also be. Can you go back one slide, Ramani? So that simplified model can, we can bring a little more complexity, by considering the fact that the wind direction is not always perpendicular to the road. So we can make some, adjustments, and then of course some work on those dispersion models is already available. Yep. One second.
Yeah.
Hello, I'm so sorry, Ramani, can you hear me?
Yeah, I can hear you. Yeah, go on.
So, so we can, either we can go with that simplified model, or, if you think that the wind direction is an important factor, we can make it, we can make that model, incorporate those effects. And then I'm showing you some early, work in that area. We could certainly adapt those models. Go ahead, Ramani, next slide.
So,
yep. So I'm going to give it to Dr. Kandiah, and then he's going to show us, how much we have already done in terms of understanding these roads and intersections, in terms of, greenhouse gases, and also these aqueous, chemicals in the air. So, and then, a lot of work has already been done in the congested areas, and then he calls them hotspots. So we have wealth of information already available, so the next step is to slowly incorporate them into our model. You take over.
So this is actually a snapshot of Ohio highways, actually for showing the work that we have done. I am demonstrating with here the data, AADT data from 2004 to 2008. So here we use MOVES, and we look into 3 greenhouse gases and 5 other pollutants, PM2.5, PM10, on monoxide, NOx, and SO2. What we are doing, as Dr. Kumar said, that when we try to use MOVES, but since MOVES is really, it takes more time to run each thing, we try to make the data kind of snapshots for the way we want, and we try to have a flat data sheet so then we can easily plug into that app. So that's the whole idea. So what we do it is, depending on the situation, we try to simplify it and find out the MOVES output for different locations. So if we come to Ohio, we look the road types into 4 groups. All of you who have worked with DOT, you might have known that already. So this is, we are looking into rural restricted road, rural unrestricted, and urban restricted, and urban unrestricted. And then when it comes to the fuels and the vehicles, we actually take all the things into 2 groups. One is passenger gasoline truck. Passenger gasoline car, we are calling it passenger gasoline truck because it's a conservative estimate. Then we are looking that into heavy duty diesel truck. So that's where we run it. That's the way we are making our database for inputting our app. So now when we look into this is actually when we did. On the left-hand side, what you see it is, this is 2 different counties. Iowa County, that is a urban county, and Morgan County, that's a rural county. How these 4 types, gasoline, passenger truck, and diesel heavy duty trucks work for different pollutant types. Here it is given per vehicle per mile how many grams of pollution actually comes on. So these are the database we are making to input to the application. Here on the right-hand side, we are doing that for the other states, also Midwestern states around here, so Illinois and other example of that one. Then a few other slides that's going to come given when we are mapping that, how it comes. So this is actually Ohio counties, and this is, first one is the carbon monoxide, second is NOx, and third one is total PM. How this concentration varies in million grams, that's what you have. So if you look into that very clearly, you can see Cuyahoga County and Franklin County, and here Butler counties. We have Cincinnati and Cleveland and Columbus they are really high, then the others are coming different. So it's basically, you see even and this is basically look into the 75, this is 70 and 71, you can see those. So that's actually and this is again the same thing for the greenhouse gases. Then this is on the roads itself, we try to show how these greenhouse gases the thicker the roads are, it is basically the emissions are high over there. So this is the idea. We try to put it inside in the app as a flat database to do the calculation. So it can be done quickly rather than running the moves every time. So that is what this is. Then what we do it is we want to look into, instead of ADT data, we also want to look how the seasonal effect, winter and summer times are down. So we are incorporating that one also in our database making. So this basically shows how the seasonal greenhouse gas emissions varying in the Midwestern states, or the average of Midwestern states, 3 different greenhouse gases. So, Dr. Kumar.
So as you have seen, from the results, we have a lot of experience running moves on various scenarios. Seasons across the seasons. Particularly in the Midwest, we have done a lot of modeling with moves, focusing on the roads and also county-wide emissions. So with this knowledge, what we could do is, once we have selected, critical intersections where traffic congestion is going to be a major issue, we would run these models and then be in a position to, come up with, kind of databases, where we have information, for that particular intersection as to how much, what kind of emission, would be happening, per vehicle basis. And then, we couple that with, either real-time data or the more currently available data in terms of traffic. So once we have the emissions per vehicle information from moves, in a way, by running model offline, and then use that information with current data, we would be in a position to get some good estimates on ambient air quality. So the whole idea is to, come up with a model that is less complex and less parsimonious, which is something that the folks who are running these servers, it's easy to understand. So we want simplicity in our modeling, and that becomes very important, when you try to develop apps, where the memory is key, in terms of how much data, we can dump, and still be able to, have reasonable predictions of air quality. Go ahead, Ramani. Once we have a model, so what are we going to do with it, the whole idea is how do we deploy them, into a mobile system, and then make it part of our, connected and automated vehicle systems. So here are some ideas, tap into our 5G phones, or radios, and then, make use of, these different technologies that CCAT is working, vehicle to vehicle, vehicle to infrastructure, vehicle to pedestrian, make use of, these services, and in terms of dating the data, traffic data. The whole idea is, when you're in a congestion, each of the vehicle is already collecting some of the data, that we can use. At the same time, we should also pull into the server, to get the data. So the whole idea is to, use this flexibility that we now suddenly have, with the connected and automated systems, to make use of that data, and then to make use of the data that is distributed, to update our model, and then through that kind of updating, make that information available to the travelers who are approaching the congestion, and then make it part of the road safety alerts that we already have. So the whole idea is, in summary, combine the traffic data currently available with a system that calculates emissions, and then use that to quickly calculate ambient air pollution, using dispersion models. So that's our strategy. That's what we are trying to accomplish. Next slide, Ramani. All right, Ramani, you want to take this one?
So here, our students at this point, they have been working on 4 different intersections around Ohio. The first one is actually, I have 2 slides next, that is intersection 75 and I-70 in Dayton, very close to the airport. The other one that we are looking into, I-71 and I-75 in Cincinnati. That is this year, 2020 is top truck bottleneck list. That is on the 8th place in the US. That is one of the things. Actually, 3 of the Cincinnati's, this one is actually on top. And the third one is actually again interstate actually I-70 and this is I-71 actually, not I-70.
Columbus area.
But, yeah, that is again 97th worst bottlenecks. And the other one is I-90 and I-70 and Cleveland. So it's a different part of the Ohio we are trying to do. The first 2 is being done by Daniel Lee, one of our students. He actually have a paper on that for the TRB conference in January, actually, as a minority fellow. And the other 2 are being done by Jasmine Walker. And this is basically Daniel Lee's one of the data from his paper. I took it on I-75 and 70 intersect. And the only thing is there's a little, when you do this traffic calculation, there's a little way we have to work with that, because where you take the data, that is going to be taking a little complexity in the whole data. I mean, if sometimes we are taking the same truck when it's going out, same car that is coming on, exiting the basic roundabout. So the intersections. That's what thing we are having in a way to calculate incoming traffic and outgoing traffic. Based on that, we will find actually how much traffic is passing through that. So that's the thing this paper is about. So it's actually submitted over there, and that's what we are at this point. The summer, actually, the students were working on further, and now we all are universities closed like everything. So they are working in remotely. So that's what we are working on with them. And that's the way we are planning to go in the summer too. At this point, we have to thank the support from the University of Michigan and the current center and the previous center, and even earlier we had with University of Akron. A long time we are going.
Hello, Debbie.
Yep. Hello. Thank you.
Dr. Kandiah.
Yeah. Let's open up the floor to see if there's any questions.
Sorry, the thing is that what happened is I am in one place and Dr. Kumar is in another place. So we are just, I am handling the topics. That's what we are just sometimes there's a miscommunication.
Also to thank, the Region 5 Center, University of Michigan, and also the people who got me in touch with these folks from Purdue. From my roots at way back, go into 90s, so when Purdue had this center. So we have been working, the uniqueness is, we are bringing into transportation, our own expertise through environmental engineering. And that's something we hope would benefit, the center in terms of its ability to, incorporate, air quality, and then, and also greenhouse gases and, carbon emissions is something that, Department of Transportation, is always looking into.
Agreed.
Decisions.
Okay. I think we're going to wrap up because we're a little bit over. And if there is no questions, we didn't see anything on Mentimeter or chat. So if you do have questions, you can email directly to the professors. But I would like to thank both professors for sharing this exciting research, and thanks to everyone for joining this special seminar series.